Okay, so let me just walk you through, and then you guys can decide. So look at this picture.
Oh,
it looks scary, right?
That's a lot of.
No. I just want you to see this picture, which looks really scary. But look at it very carefully. All this scary looking picture is showing you is we have the same tunnel that comes in, this tunnel, right? That's going in. And we are just trying to figure out how many of these particles that are coming in will be scattered in this patch. That's all we're doing. And this patch actually will just be redefined as a ring of fire that goes around the sphere. And these are the same ones we've done before. That's theta over S, that's V, that's theta scattering, that's V initial, and that's V final. That's all there is. We've done most of it. Do you guys want to quickly do it? So when we do a calculation like this, what do we need? How many particles are scattered into this patch? So we have to redefine what this patch is. And the patch redefinition is easy. We did this, right? R, S, theta for a circle. When it becomes a sphere, how does this change? S equals R theta. But when you have a sphere and you're trying to find the patch, it is actually called a solid angle. Heard that term before? And solid angle, usually people write it as that. That's all there is. So if you were to take that tiny patch, may I call this patch the tiny d of sigma? That is defined as the area of the patch divided by the radius of your sphere, squared. So what is your patch area? R d theta, R sine theta d phi. Stare at it very carefully. We have done this before. This is just in 2D. When you have a sphere, what are your coordinates? R theta phi. Remember? We defined it as dr, r d theta, r sine theta d phi. Do you remember doing that? When we did volumes? This is exactly the same. So I'm not doing anything else fancy. We have developed to this point where I don't have to explain that math to you. I hope.
why are you doing two parts though?
Why am I doing two parts? Because R is a constant. And I'm defining the patch. So the patch, so I'm only looking at this patch right here.
Yeah.
So this patch has two sides. The R is on the outside, right? That remains constant. So I just have to worry about this side and that side. So it's the patch on the sphere. The R is a constant, but that patch could move. And so the two angles that will move are the theta and the phi. Does that make sense? Yeah. So those are the two sides I'm worried about. But R is on the outside. R won't change. Unless I physically change my sphere, then R will change. Then I have to do the dr.
Why are you splitting it two terms when we do the volume? We have just one big term of the all.
No, it's not the volume. It's just the surface area.
Okay.
The
So
patch lies on the surface area.
why would you split up two terms of the patch area?
Oh, the patch area will just be the theta component and the phi component.
That's
Yeah, so we have to split them up. There's going to be a phi. How far away is it from the theta, and then how far away is it from the azimuthal angle? Those are the two patches we're going to worry about. Or I can rewrite this as R goes away, and I will get d theta sine theta d phi. We've done this in like 3 different chapters. We did it for the moment of inertia. We did it in chapter 1 twice, the d thetas and the d phis. Okay, then the other thing that we worry about is this patch, the patch in the red. How many particles are there to begin with? And we call how many particles there were to begin with a fancy name called d sigma. What was sigma that we just defined before? Started with an S? Scattering cross-section. It's the same one. So these are the particles that are incident on it that are found in this red patch. That has now become a blue patch. Good? So these are the particles that came in from there. Watch carefully. How do I define this? This is defined as dB times b d phi. It's this dB in this patch plus this d phi. But that's total b, and that's the little tiny b that we're worried about. So think about it sort of in 3-dimensional. I'm just looking at this patch going forward. Right? This tiny patch going forward. And again, it'll be in 2D, defined as that. So then may I rewrite this as b dB d phi? We actually calculated b before, like here.
Yeah. We did that.
And we calculated dB here. Can I plug them down there?
No.
Sure. Wow. Okay, so is b,
It is R plus RH cosine of the scattering angle over 2.
and what was dB?
R plus RH over 2. Negative. And then sine scattering angle over 2 d theta equals.
And it was d, what was it? D theta?
Yeah.
And d phi still exists, right?
Yes.
So will this simplify to r plus rh squared divided by 2? Remember the 2 is on its own. Cosine theta s over 2 sine theta s over 2 d theta d phi. Oh, there's a minus sign. Thank you. And that's d sigma. Can I combine these together somehow? Does trig allow me to do that? You want to remember that formula? This is sine theta over 2. So will this not become sine of 2 times theta s over 2 divided by 2?
We are really slow.
We're just a little slower.
There we go. Right? So far, so good?
Now.
Now this will get canceled. Will I now get what I was getting before? R plus RH, now divided by 2 squared, right? There's a square here, 2 here, and a 2 here. Can I combine those 2's together? And then put them all, like there'll be 4 squared, so far so good. And then I will have sine of theta s, d theta d phi. I should probably call them either sine, this should be S2, right? S. Oh yes, minuses. Those I forgot. Okay. So now this is a term you would have seen before if you've done quantum mechanics. It is called differential scattering cross-section. That is a very scary looking word, right? But all that means is d sigma over d omega. What's the value of d sigma? I'm just rewriting this again. And what was d omega? Somewhere here, right there. Yes? May I plug that in here? But this time I'm going to call them ds. Forgot already. Sine and d. Sine of theta s and d phi. Watch magic happen. And what are we left with? Drum roll, please.
Why is it negative?
And in general, people, when they talk about differential scattering cross sections, they talk about absolute values. They don't want to worry about the negative sign. So if I put an absolute value here, what happens to my minus sign?
That's a cop out.
I know. What do you think that's so cool about this? What does it not depend on? It depends on none of the angles. It literally only depends on the R's of the particles that are interacting. And do you want to know what the actual total differential cross section will be? Please don't murder me when I tell you.
Oh, yes.
Yes,
Is it the area of the tunnel?
it's the area.
Now can I have my degree?
Now you can have your degree. But literally, this is the differential cross section. How do you go from a differential cross section to total cross section? You integrate, correct? Let's integrate this.
Wait, I still need to write things down.
And Amanda's already given the plot line away.
Sorry.
Yes? Oh, and magnitude. Not worrying about this. Will these two go away? Am I left with d sigma? And it's double integral 0 to pi, 0 to 2 pi. Yes? So if I take this value and I plug it in here, I do a little bit of differentiation, and guess what I get? So the moral of the story is, we have done nothing new. All that math to do nothing new. Did we not start by this definition here today? They're all going to kill me now.
Oh.
But you know what's fascinating about it? We came up with the same answer. Had we come up with a different answer, things would not be right. That should make you feel better. I'm going to clap for myself. No one else will. That brings us to the end of what I wanted to do today. There is more math in the textbook. It will be in your interest to do that because one of them will show up on the final.